Hello everybody, it's your friend Daniel here and welcome back to another past paper video. In this video we're going to be going over the specimen paper for AQA GCSE Chemistry Paper 2 and we're going to be going over the higher tier. Now without further ado, let's jump straight in. For question 1 is about halogens and their compounds, and table 1 shows the boiling points and properties of some of the elements in group 7. And we're just given no information about the colour, boiling point and the element. And we'll ask, why does iodine have a higher boiling point than chlorine? And this is due to the forces between the iodine molecules being stronger. For 1.2, we're expected to predict the boiling point of bromine, and because bromine is between chlorine and iodine, we'd expect it to be somewhere in the middle. I went for around 80, but they'd accept anything in the range of 30 to 120. And then we're given a redox reaction. It takes place when an aqueous chlorine is added to potassium iodide solution. The equation for this reaction is this. And we're asked to look at table 1, what is the colour of the final solution in this reaction? And now if you look at table 1, you can see that iodine has a brown solution, so the colour is brown. And for 1.4, we're expected to work out the ionic equation for the reaction of chlorine with potassium iodide, which is 2I minus plus Cl2 goes into I2 plus 2Cl minus. And then why does potassium iodide solution conduct electricity? And this is due to it contains ions which can move. Lots of multiple choice questions, but this is the last one of question 1, I believe. What's the products of electrolyzing potassium iodide solution? The product at the cathode is hydrogen and the product at the anode is iodine. With this just being something you need to remember, you need to do a bit of research into electrolysis and work out the order of what reacts with what, and what reacts at the cathode and what reacts at the anode. Next up, we're given an atom of aluminum with the symbol 2713Al, and we're expected to give the number of protons, neutrons, and electrons in this atom of aluminum. Now, 27 is the atomic mass, which is the sum of protons and neutrons, and 13 is the atomic number, which is just the amount of protons. So as I said, the number of protons is 13, but if 27 is the sum of protons and neutrons, then there must be 14 neutrons, and unless it's an ion, the amount of electrons is always the same amount as the amount of protons, which means the number of electrons is also 13. And then we're asked why it's positioned in group 3. Now, as you remember, the group number refers to the amount of electrons in the outer shell, and that's because aluminum has 3 electrons in its outer shell / energy level, meaning it's in group 3. Then next up, we're given some transition elements and group 1 elements, and we're given their information in the table and expected to compare them. We're asked to use our own knowledge and the data in table 2 to compare the chemical and physical properties of transition elements and group 1 elements. Now, beyond information in the table means that you don't just talk about the melting point formula of oxides, you talk about other physical and chemical characteristics. Now, for their physical characteristics, transition metals have high melting points and high densities and are strong and hard. This is in stark contrast to the group 1 metals, which have low melting points, low densities, and are soft. Now, you may remember watching a video where you can cut a group 1 element with a knife. And for chemical, transition metals have a low reactivity and form ions with different charges, while group 1 metals are very reactive and can only form +1 ions. Now, for an actual 6 marker, I wouldn't have these like headings, but I'd just write it as full sentences. But I believe for the purposes of going through a paper and explaining it, it's best to have them as physical and chemical. Next on question 3. Figure 1 shows the outer electrons in an atom of the group 1 element potassium and in an atom of the group 6 element sulfur. Potassium forms an ionic compound with sulfur. Describe what happens when 2 atoms of potassium react with 1 atom of sulfur, given your answer in terms of electron transfer. Now, electrons transfer from potassium to sulfur. Two potassium ions each lose one electron, forming two K plus 1 ions, and then the sulfur atom would gain 2 electrons, forming S2 minus ions. Moving on to 3.2, the structure of potassium sulfide can be represented using the ball and stick model in figure 2. The ball and stick model is not a true representation of the structure of potassium sulfide. Give one reason why. Now, as you can see, there's lots of gaps and like these sticks used to explain the gaps, while in a real potassium sulfide structure, there would be no gaps or sticks between the potassium and sulfide ions. Now moving on to 3.3, self-conformed covalent bonds. Complete the dot and cross product to show the covalent bonding in a molecule of hydrogen sulfide. Show the outer shell electrons only. Now, for them to be reacting in the covalent bonding, they each have to have a full outer shell. So we can see they share one electron, so each hydrogen has 2 electrons in the outer shell, and for the sulfur, it borrows 1 from the hydrogen, so they have 8 electrons in its outer shell. Okay, moving on. We're expected to calculate the relative formula mass of aluminium sulfate. Now what you do is you just get the components and add together. You have 2 aluminum and then 3 lots of SO4, so 2 times 27 plus 32 plus 16 times 4, all times by 3 to get your answer, which is 342. Next up, just a couple of multiple choices where we're given the properties of stuff. Covalent compounds such as hydrogen sulfide have low melting points and do not conduct electricity. Give one line from each property to the explanation of the property. Now the reason for a low melting point is weak intermolecular forces of attraction, and the reason it does not conduct electricity when molten is there are no charged particles free to move. And for the other one, we're talking about ionic compounds, and the reason for a high boiling point is the bonds are strong, and the reason it conducts electricity when molten is ions are free to move. Next up, for question 4, we're given a few steps about process of a student separating rock salt from just separating the rock and the salt sand, and we're just given the process, and we're asked to suggest one improvement to step 2, which is to add 100 centimeters of cold water to make sure all the salt is dissolved. Now I don't remember if none of you guys have probably had coffee, or at least very few if you would have done. But one improvement is that if the salt is dissolved in the water, salt dissolves better in hot water. So like, have you ever tried to dissolve instant coffee in cold water? It doesn't dissolve that well. However, if you try to dissolve instant coffee in hot water, it works really well. The same applies to all processes of dissolving. So to make sure that all the salt is dissolved, just heat the water. And salty water in step 4 still contains very small grains of sand. Suggest one improvement to remove all the sand. And this, instead of just carefully pouring the salty water and hoping none of the sand gets into it, you could just filter out the sand. And suggest one safety precaution the student should take in step 5. Now, you can see in step 5 they heat the contents. So what you need to do is you need to wear safety goggles to make sure like no salt water splashes up into your eyes due to it boiling or something. Although it probably wouldn't be boiling. No, it probably would be boiling actually. And another student removes water from salty water using the apparatus in figure 3. Describe how this technique works by referring to the processes at A and B. Now at A, you can see the salty water is being heated, which means it would evaporate. And in B, there's a long tube where it would cool down and condensate and be pure water. So my answer is the water evaporates into a gas at point A before condensating at point B as pure water. And what is the reading on the thermometer during this process? 100 degrees Celsius. Because you want it to be high enough for the water to evaporate, but you don't want it to be so high that the water doesn't cool down in the tube. Now on question 5, a student investigated the reactions of copper carbonate and copper oxide with dilute hydrochloric acid. In both reactions, one of the products is copper chloride. Describe how a sample of copper chloride could be made from copper carbonate and a dilute hydrochloric acid. Now what you do is you add excess copper carbonate to dilute hydrochloric acid. And what I mean when I say excess is add until there was copper carbonate powder left over in the beaker that has not dissolved. And then you filter to remove this excess copper carbonate from the solution. And then you heat the filtered solution to evaporate some water, or heat until the point of crystallization, then leave it to cool so crystals form. Now for 5.2, a student wanted to make 11 grams of copper chloride. Then we're given the equation for the reaction, and we're expected to calculate the mass of copper carbonate the student should react with dilute hydrochloric acid to make 11 grams of copper chloride. But firstly, we want to work out the molecular mass of copper chloride, which is 134.5. And then the moles of copper chloride is the mass divided by the molecular mass, which is 11 divided by 134.5, and then you get 0.08178. And because the molar ratio of copper chloride to copper carbonate is 1:1, you also need the same amount of moles of copper carbonate. And you work out the molecular mass of the copper carbonate and times the amount of moles by the molecular mass. So you times 0.8178 by 123.5 to get 10.1 grams. And then we're given that the percentage yield is 79.1%. So for copper chloride, and because there's 11 grams of copper chloride that the reactions should get, you just times 11 by 0.791 to get 8.7. Then we're given the equations of the two reactions, and then we're asked to calculate the percentage atom economy for reaction 2. So, as you know from the previous question, the molecular mass of copper chloride is 134.5, and then you add on the molecular mass of H2O, which is 18. So the total mass of reactions is 152.5, and then you simply do 134.5 over 152.5 times 100 to get the percentage atom economy, which is 88.2. And then we're given the atom economy for reaction 1, and we're expected to explain why it's less. Now the reason it's less is, as you can see, there's more products. So less of the products are made up by copper chloride. And you can see I'll explain this. The atom economy using carbonate is lower because an additional product is made due to carbon dioxide being made as well as water and copper chloride. And then we're given for question 6, we're asked to investigate simple cells using the apparatus shown in figure 4. If metal 2, which is here, is more reactive than metal 1, the voltage measured is positive. If metal 1 is more reactive than metal 2, then the voltage measured is negative. The bigger the difference in reactivity of the two metals, the larger the voltage produced. And we're given the results here, and then we are asked to explain why the zinc is oxidized. And what you need to remember is the acronym oil rig. Oxidization is loss of electrons, and reduction is gain of electrons. Now, as you can see here, the zinc is losing electrons, which means it's being oxidized, and you can see I explain that in my answer. As the zinc loses electrons, and since oxidization is the loss of electrons, and since the zinc loses electrons, it's therefore oxidization. And then we're asked to table 3 to show which one is the least reactive. Copper, and that's because it gives the largest positive voltage when metal 1, with 1.2 being the largest positive voltage when out of all of them. And when used as metal 2, it gives off the largest negative voltage. And we're asked to predict the metal that would obtain for a simple cell that has iron as metal 1 and copper as metal 2. Now, the voltage with chromium and copper is 1.2, and the voltage with chromium and iron is 0.5. Which means there's a voltage difference between iron and copper of 0.7. And since copper is less reactive than iron, and it's being used as metal 1 instead of metal 2, it's minus 0.7. Next up for 6.4. Hydrogen fuel cells have been developed for cars. Write a word equation for the overall reaction that takes place in a hydrogen fuel cell. And that's just hydrogen plus oxygen equals water, with this just being something you need to simply remember. And then we're expected to write out the two half equations, which is that H2 goes to H2 plus 2E minus, and then O2 plus 4H plus 4E goes into 2H2O. Now for question 7, sodium carbonate reacts with dilute hydrochloric acid, and they give you the formula for that reaction. And we're asked to investigate the volume of carbon dioxide produced when different masses of sodium carbonate were reacted with dilute hydrochloric acid, and then they just give you the method for it. And then they give you the setup that the student uses, and we're asked to identify what's wrong and what would happen if they used it as shown. Now what's wrong is that the delivery tube is in the water, meaning the acid would go into the water, messing up the experiment. Then when the student corrects the error and does the experiment, we are given the results, shown here. And then we're shown that the result of 0.2 grams of the sodium carbonate is anomalous, as shown by 0.2 grams only produces 12.5, which is much less. And then we'll suggest what may have happened to cause this anomalous result. I wrote, there's many answers, but I wrote that the bung may not have been fitted properly, allowing the carbon dioxide gas to escape. So like this top thing that's sticking on may not have been fitted properly, allowing this carbon dioxide gas to escape and not be measured correctly. And what further work could a student do to be more certain about them? Oh wait, I missed 7.3. Why does the volume of carbon dioxide collected stop increasing at 95? And this is due to all of the acid reacting, meaning no more gas is being produced. And a good way to think about this is that before this, the acid was in excess, but after it, the sodium carbonate is in excess. And then we're meant to ask what further work could the student do to be more certain about the minimum mass of sodium carbonate needed to produce 95 centimeters cubed of carbon dioxide. And this would be to take more readings in the 0.34 to 0.54 range. Then for 7.5, we're asked how many moles of carbon dioxide is in 95 centimeters cubed, and that 1 mole of gas in room temperature and pressure is 24 decimeters cubed. Now 24 decimeters cubed, to get into centimeters cubed, you times it by 1,000. That's just realised that's meant to be cubed. And that's 24,000 centimeters cubed, and then you simply do 95 over 24,000 to get the amount of moles, which is 0.00396 moles. And then suggest one improvement that can be made to the apparatus that would give more accurate results, and that would be using the gas syringe to collect the gas so it will not dissolve in water. And as you can see in the figure, they use it in a measuring cylinder, and some of the gas, some of the carbon dioxide, could dissolve in the water. However, if you just attach a gas syringe on top, there'd be no water for it to dissolve in too. Secondly, one student said that the results of the experiment were wrong because the first few bubbles of gas collected were air. A second student said that this would make no difference to results. Explain why the second student was correct. And I said that the bubbles of air should be collected because carbon dioxide is left in the flask at the end and it has the same volume as the air collected in the gas syringe. And if I quickly go back to the figure, I can explain. Now in the flask at the beginning there's air, but as carbon dioxide is produced, this air gets pushed into the measuring cylinder. However, at the end of the experiment, there's carbon dioxide left in the flask. But since the volume of carbon dioxide in the flask is equal to the volume of air that gets pushed into the measuring cylinder that isn't carbon dioxide, the measurement of air in the measuring cylinder is equal to the volume of carbon dioxide produced. Next up for question 8, sodium hydroxide neutralizes sulfuric acid. The equation for the reaction is 2NaOH plus N2SO4 into Na2 plus SO4 plus 2H2O. and then we're asked what is the definition of a strong acid, which has just been a definition in your textbook that you need to remember, and that is an acid that is completely ionized when dissolved in water. And then we're expected to write out the ionic equation for the neutralization acid reaction, including state symbols, which is H plus H plus, which is Aquarius, plus OH minus, which is Aquarius, into H2O, which is a liquid. And then we're given a quick titration question asking you to explain how the student will complete the titration and name a suitable indicator on color change, which is you add a litmus indicator to the sodium hydroxide in the flask, then add the acid from a burette, then swirl until the indicator changes from blue to red. And yes, that is all you need for a 4 marker. It is ridiculous. AQA, this is a sample paper, so it was never meant to be sat by students, but it is still a bit ridiculous to have a 4 marker that can be done in 1.5 lines. And then we're given the titrations that were completed and expected to find the mean of the concordant results, with the concordant results being results that are within 0.1 centimeters cubed of each other. And as you can see, the titrations 3, 4, and 5 are within 0.1 centimeters cubed of each other, and then we just calculate the mean of them. You guys know how to calculate a mean. It's just 27.12 centimeters cubed. Then finally, on 8.5, we're given a bit of a maths question. We're expected to calculate the solution of sodium hydroxide. Give your answer to 3 significant figures. Firstly, we need to work out the moles of sodium hydroxide, which is the concentration. No, right, that's not sodium hydroxide. Firstly, we need to, I'll just say the letters. Firstly, we need to work out the moles of N2SO4, which is the concentration, which is 0.1 from earlier in the question, times the volume, which is 0.02712 from earlier in the question, with that getting you 0.00271. And then you can see that the molar ratio is 1 to 2. So for every mole of H2SO4, you need 2 moles of sodium hydroxide. So you need 0.00542 moles of sodium hydroxide. And then the concentration is the amount of moles over the volume, which, as stated earlier on in the question, was 0.025 decimeters cubed, or like 25 centimeters cubed. So you just get the mole value divided by 0.025 to get your answers of 0.2168 moles per decimeter cubed. And then for 8.6, the student did another experiment using 20 centimeters with a concentration of 0.18 moles per decimeter cubed, and we're given the relative formula mass. So firstly, we work out the volume in decimeters cubed, which is 20 over 1,000, and then we times it by the concentration to get the amount of moles, which is 0.15 moles, and then we just times the moles by the molecular mass to get the mass, which is 0.144 grams. Finally, on question 9, sort of question about reactions between ethene and bromine. We're given the reaction and then we're expected to draw an energy profile. Thankfully, they give us the 2 lines, so you just need to draw the little curve, label the activation, label the energy given out, and this is an exothermic reaction due to the final state being higher than the final state being lower than the starting state. Then with 9.2, when ethene reacts with bromine, energy is required to break the covalent bonds in the molecules. Explain how a covalent bond holds 2 atoms together. And there is an electrostatic force of attraction between shared pair of negatively charged electrons and both positively charged nuclei holding the atoms in the molecules together. And we're given figure 7 in a table showing the reaction of ethene with bromine, and we're expected to use the information in table 6 and figure 7 to calculate the bond energy for the BR-BR bond. Now what it is that the overall energy change is minus 795, which means that the bonds broken minus the bonds formed equals 95. So firstly, we calculate the bonds formed, which is 2,548 kilojoules per mole. Then we do the bonds broken, which is all this, which is 612 plus 4 times 412 plus the BR-BR bond minus the bonds formed, which is 95 kilojoules per mole. And then we can simply rearrange to get the BR-BR bond, which is 193 kilojoules per mole. Finally, figure 8 shows the reaction between ethene and chlorine and is similar to the reaction between ethene and bromine. And then we're given a bit of preamble just to help us with the question. The more energy levels or shells of electrons an atom has, the weaker the covalent bond that it forms. And we're expected to use the above statement to predict and explain how the overall energy change for the reaction of ethene with chlorine will differ from the overall energy change for the reaction of ethene with bromine. And I'm just going to read out the question, read out the answer. Chlorine atoms have fewer electron energy levels than bromine and therefore form stronger bonds. This leads to the Cl bond being stronger than the Br-Br bond and the CCl bond being stronger than the CBr bond. This leads to the energy being required to break bonds with chlorine being greater, and thus more energy is given out when making bonds with chlorine, with the overall energy change depending on sizes of energy change. But since both the energy to break and form the bonds increases, we won't be able to tell how much the overall energy change differs, as we won't know which would increase more. So basically, using chlorine instead of bromine increases the energy required to make the bonds, but also increases the energy required to break the bonds. However, we won't be able to comment on the overall energy change without knowing which one it increases more. Anyway, that's the end of the paper. Hopefully you enjoyed it, hopefully it was helpful, and make sure to like and subscribe and turn on the notifications to get more information about when I release both past paper content and topics. Anyway, this is Daniel, signing out.